In this lesson, we will look at the design and construction of retractable main landing gear. The majority of modern transport aircraft and an increasing number of light aircraft are fitted with a retractable landing gear for the simple purpose of improving aerodynamic performance by helping to reduce drag in flight. Operating power is normally provided by a hydraulic system, but pneumatic or, on some small aeroplanes, electrical systems are sometimes used. A retractable landing gear is provided with mechanical locks to ensure that each leg is locked securely in the up or down position. It will have a means to indicate to the crew the position of each leg and a means by which the landing gear can be lowered in the event of the failure of the normal power system. In addition, a system is provided to prevent retraction with the aircraft on the ground, and warning devices are fitted to help guard against landing when the gear is retracted. For aerodynamic reasons, wheel wells, which is where the wheels are housed, are normally sealed by doors which close after the gear is up. For the same reason, some of the doors may also close after the gear is locked down. This picture here shows the closed main gear doors on a Boeing 747. The geometrical arrangement and physical location of landing gear units on aircraft is by no means standard. The type, size, and position are decided at the design stage, having already taken into account the many factors that must be considered. The main considerations are the size and weight of the aircraft, the role the aircraft will fulfill, whether it has a high or low wing, and any associated gear stowage problems. Most modern aircraft will have the main landing gear attached to the wing, with some of the larger types having both wing and body gear. The body gear itself may actually still be steerable. This helps to reduce the turning circle and reduces the effect of wheel sideways movement or tire scrubbing, which affects multiple wheel landing gear systems. A number of aircraft are designed to operate in the dual freight and passenger carrying roles, especially from airports with limited resources. This has resulted in high-wing monoplane type aircraft where the floor of the aircraft is as close as possible to the ground for ease of freight loading. However, with some wings being as high as 6 or more meters off the ground, it is impossible to build a landing gear of sufficient strength to reach this far. So these aircraft incorporate the main gear in the fuselage. The diagram here shows a typical large aircraft retractable wing gear. The leg is attached to the wing spars by a cylindrical beam or trunnion on which the leg is free to rotate laterally. The upper part of the leg forms the outer cylinder of the oleo-pneumatic strut. The strut in a cylinder is connected to the wheel bogie or truck beam. The truck beam is able to pivot about its central point in a controlled way, as you see here. This allows all main wheels to be on the ground with the fuselage in the takeoff or landing attitude. There is an axle connected to a pair of braked wheels at each end of the truck beam. The wing gear torque links prevent rotation between the shock strut inner and outer cylinders, without affecting their reciprocating action during normal operation of the strut. The drag strut, as shown here, supports the leg in a fore and aft direction. The upper and lower side struts support the leg laterally. They fold out when the gear is lowered, and are then held in place by the jury strut, which also folds out during extension. The jury strut is pulled over center by the downlock actuator, geometrically locking the gear down. If the gear is lowered without hydraulic power, then the over-centering action will be performed by an internal spring in the downlock actuator. To review the purpose of any of the components we've just mentioned, click on the appropriate label. For aircraft with the landing gear built into the fuselage, the requirements are basically the same as those for wing-mounted landing gear, except that often the gear mechanism may not be long enough for geometric lock to be available, so an alternative provision has to be made for locking the gear both up and down. Depending on wheel layout, each wheel may require its own shock absorber unit, and possibly even a steering motor. A landing gear unit has to withstand various loads during its life. These loads are transmitted to the mountings in the aircraft structure, so these too have to be very strong. A landing gear is also subject to compressive loads, particularly during landing, but also whenever the weight of the aircraft is on the ground. The oleo-pneumatic strut helps to cushion these loads. The gear is also subject to rearward bending loads during braking. These loads are taken by the drag strut. There are also side loads during crosswind landings, also during takeoffs and taxiing. These loads are taken by the side struts. The nose gear is subject to longitudinal loads during pushback and towing. Again, these loads are taken by the drag strut assembly. You should now be able to identify the various components of the main landing gear, as well as understand their purpose. You should know, for instance, that the torque links take the main landing gear torsion loads during ground maneuvering, and that some larger aircraft have a steerable body gear, and that lastly the gear is normally locked down by a geometric lock produced by the over-center movement of the jury strut.